Hey, it's time for us to get started. Last week, we started talking about grammars and what grammars are, how to write them, how to read them, what they can do for us. We had a couple of different solutions for this particular exercise that we looked at. Did anyone have any questions? We all recall what grammars are, what these productions mean, how they solve the problem at hand. How this relates to recursive thinking, didn't really bring that up in class, but in the solution that we looked at, where we had S arrow A, S, B, and S arrow B as two different productions that we could use off of S. When you have something like S arrow lowercase a, capital S, lowercase b, that's kind of recursive thinking, where we're defining something in terms of itself. So maybe this ties back to an algorithms class that you've taken in a way that may help you to think about it or visualize it as well. So today we're going to start diving into what automata are. And as we finish this, we're going to start in with our first kind of automata that will recognize a particular class of languages. This is the first class of languages that we will talk about. So automaton is the singular, automata is the plural. An automaton, as I think I mentioned on the very first day, is just an abstract model of a digital computer. We have states, we have transitions, so let's figure out exactly what this thing is. The idea is that it will read input. In this case, it'll just read a string. And it will go character by character through that string. And as we read those characters, we will be at certain states, making transitions based off of the input character. And from that, we will eventually reach an accepting state or a non-accepting state. But this is just one of the two classes of automata. This is an acceptor. There's also a transducer that can actually produce output, rather than just the binary yes or no. So we have a given input alphabet that is the language of the strings that we would like to read. So in practice, this is usually binary or hex or English or some language that we actually use and recognize. The first couple classes of automata that we will talk about, this is very much true. We are going to read the string character by character. We can't go back through the string. So we need to do all of the, what is it I want to say? All of the thinking that we're going to do in the machine. All of the instructions are going to be done on the current character, and we cannot, at least to start with, we cannot store that character. We cannot store anything. We're just going to have to make a decision about where to go and what to do. Note that the last thing there is pretty important. We can also detect the end of the input. So we know when we are done reading input. So we have some mechanism for reading input. We have some mechanism for producing output to some storage device. For now, we assume that that output has an unlimited amount of storage. So we don't have the limitations of our current digital computers with regards to a finite amount of RAM or a finite amount of hard disk space. For now, we just assume we have an infinite amount of output storage. There's also a control unit. The control unit is a finite number of internal states, and we can modify those states before we run the system. So in the same way that we would write a program and be able to modify that program for its execution, we can modify these internal states and they will accept a different language. So to visualize one of these, we have an input file of some number of characters, each of which belong to the input alphabet. The control unit reads the input file. The control unit is going to be calculating what internal state it is in and shifting between those states based off of what it sees in the input file. As it does this, it may or may not be writing to this infinite storage. And at the very end, it stops or it doesn't. So it is possible for something like this control unit to continue spinning forever on a particular input. This is what you might expect when you run a program that has an infinite loop. This program does not halt. So if you were to feed that program to this automata, since it's a representation of a digital computer, it would also be moving from state to 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 state, never reaching a termination condition. So just a representation of a digital computer. You can think of the input file as command line arguments, some file that you write to read from, the control unit as your program, and the storage as whatever is displayed to the console, written to a file, or whatever the output from your program is. We operate in discrete time steps, which is why discrete is such an important part of this class. So there is a time step 1 where we're looking at the first character. Based on that, we may be moving from state to state in the control unit. Every time we make one of those transitions in the control unit, or we make a transition from reading a character in the input file to the next character in the input file, we state that the time step has increased. So at any given time step, we can take a snapshot of the internal state of this automaton. We know where the control unit is. We know what state it is in. We know where we are in the input string. We know what the current character is that we are marking. Because of this, we can use a Markov decision process, basically, to determine, given the current state and given the next character to be processed in the input string, we can define a transition function that tells us, given these two important pieces of information, where is the next internal state going to be? Do we shift from the current, if we go back to the control unit is in a particular state, do we switch the state the control unit is in? Do we stay in the current state? The state character in the input file pair determine that systematically. Does that make sense? Questions about that? State input pair tells us what the next state is going to be. We'll get plenty of examples of this. So as we do this transition, we may or may not produce output. So that way, we can take a snapshot of this in any particular moment of time, talking about the automaton's configuration. The configuration is just a tuple of the control unit's state, the position in the input file, and all of the storage at the current point in time. We can define the concept of a move as this process, the transition from one configuration to the next configuration, based on the character in the input file. We're going to talk about lots of different types of automata, because they represent different classes of languages. So we want to make this as simple as possible if we are trying to look at or understand or represent a simpler form of language. And they get more and more complicated as we want to kind of move out our view and have more and more complicated types of languages. We're going to break them down into two. We'll get there. The first one we're going to talk about is a deterministic automaton. And this tells us that the transition is uniquely defined. Meaning that if we actually have a configuration of an automaton, then we know for sure what the next configuration is going to look like. And the next configuration, and the next configuration, and the next configuration. It works in a predefined manner. This is exactly what all of our computers do. Our computers are deterministic. If we write a program, we know what the output of that program is going to be, or we can figure out what the output of that program is going to be before we run it. Right? If I have a program that has a function that is perfectly written with a function called add, it takes two inputs, number 1 and number 2. It adds those two and returns the output, and I feed it 3 and 2. Before we start, we know the output of that is going to be 5. It can't be anything else. There's another kind of automaton that we're going to talk about probably tomorrow or Wednesday, depending on how quickly we get through some stuff. A non-deterministic automaton. Has anyone heard of or looked at in some other class non-determinism? It's a freaky concept that we're going to talk about after we talk about it, our first deterministic automaton. I'm going to take some time quite a bit of time to describe non-determinism because it's really strange. So if we are in a particular configuration, there may be multiple possible next configurations. Because of this, it's really difficult to figure out what a particular automaton is going to do or can do based on a particular configuration. This is not how our computers work. It's a completely theoretical model that may become practical at some time, but we can also kind of switch between a deterministic mindset and a non-deterministic mindset, and we'll talk about what that can do for us. I've hinted at this, but there are two other major classifications of automata. We have acceptors that give us a yes or a no. The purpose of an acceptor is to tell us, yes, the string is in the language that this automaton accepts, or no, this string is not in that language. There are also transducers. Transducers actually produce real output. That's not just a yes or no answer. In this class, we are almost completely going to be focusing on acceptors. We will talk about transducers later. They're much more complicated. Questions about any of these classifications? I didn't want to spend too much time fully describing this concept because I have to do it at an abstract level. I want to use the concrete example of a particular kind of deterministic automaton so that we can actually walk through this process with some examples. Before we get to that though, let's talk about some ways we can use these. So far we've talked about formal languages, this concept of having an alphabet, reducing the star closure of that alphabet down into some language that represents a subset of that star closure. We've talked about grammars and we've talked about automata. Where are these actually used? This can feel like a very abstract class at times because we're talking about very abstract ideas. I want to make sure that at every point in time, we have at least some tie to real world applications of what we are talking about. So syntax diagrams for programming languages, if you're designing a language, you're trying to understand a language, and we want to be able to determine the syntax, the legal syntax, or visualize the syntax of a language. Writing grammars. I showed you the grammar for the Java programming language last time. Of course, compilers, the main name of this class. It's hard to talk about compilers without being able to talk about, okay, we need to figure out, yes or no, this program is in this programming language. You write something in some programming language, let's say it's Java, and we want some program to say, yes, this program is in Java, or no, this program is not in Java. Because why try to compile a program that has a syntax error? we're not going to be able to do it. The compiler is not written to convert something that is incorrectly written into machine instructions. It has to be in Java in order for the compiler to be able to do its job. So being able to say, yes, this program is in Java, or no, this program is not in Java is very important. We may also want to be able to formally verify a program and say, you say that this program for all inputs is going to be able to produce exactly this potential output. There's some input to output function. That is what you say you have written. Does it actually do that for all infinite inputs that it can accept? Yes or no? You could write a unit test for that, but a unit test would only verify a particular input. So you would need an infinite number of unit tests to be able to prove this. None of us have infinite time, so we would need to fall back on an abstract digital model of a computer to be able to say yes or no. And in fact, we can reason about an infinite number of inputs given the tools that we will talk about in this class. Maybe we also want to write a program that takes as input a Java program and spits out as output a Python program. Or vice versa, or some other language to language conversion. Maybe we want to be able to specify English logical instructions for a Java program. You could do that with these tools. At a more low level, binary adders. This is an example of an actual transducer instead of an acceptor. I wanted to throw at least one example of a transducer on there because a binary adder takes as input two binary numbers and spits out as output one binary number. So this is not just yes or no, we actually want as output ones and zeros. If I asked any of you to add two binary numbers, what process would you take to do that? Something really simple, with a couple of 3-digit numbers. 101 and 110. And how would you add these two binary numbers?
Convert it to decimal, then add it, then convert it back to binary.
Gross, don't do that. We could use a few rules, right? So we have the two input, let's call this I sub 1, input 1, I sub 2, and we want the output digit and we want the carry. So if we have 0 and 0, we write a 0 and we carry a 0. If we have 0 and 1, we output a 1 and we carry a 0. If we have 1 and 0, we output a 1, we carry a 0. If we have 1 and 1, we output a 0 and carry a 1. Right? This is a logical AND. This is a logical XOR. So we could use these rules to basically do what you might be used to in base 10. Here's where the output goes, and kind of up here is where we think the carry goes as we're actually going through this process. So we see as input a 1 and a 0. So we see 1 and 0. So we want to output a 1 and carry a 0. Now we actually have 3 inputs because we want the carry to feed back around as a potential input to the next iteration. So we have a 0, and a 1. So this is equivalent to the 0 and 1 case. So we're going to write a 1 and carry a 0. We see a 1 and a 1, so we're going to write a 0 and carry a 1. And then the carry feeds back around. We have the equivalent of 1 and 2 zeros. So 1 and zeros, we write a 1 and we carry a 0, which ends up canceling out. There's our answer. 1 0 1 1, assuming that, of course, these are positive, this isn't 2's complement, et cetera, et cetera. But you can now see that we have a process that takes input and produces output. So a binary adder can be visualized as basically a transducer. You can imagine now that these are a bunch of states, right? This state 1, 0, we would select, this is the current state that we are in. So we're going to produce this output, store this, and we would be able to figure out based on the inputs what the next state is going to be. The next state, when we carry a 0 and see as input a 0 and a 1, we're going to move from this state to this state. So each row of this represents a state that we are in when we're figuring out the end result of this calculation. Does that make sense? Questions about how to visualize that as a problem in terms of states? The current input characters rely on figuring out which state we are in by looking at the input. We transition from state to state based off of the input that we read. As we do that, we produce some output. And by the end of that, the output determines the answer to the problem. It's just a representation of exactly what a program does. All right, end of slide deck number 2. I'll upload these later today. One other thing that you can expect is that your first assignment will be posted today. I did mention that Wednesdays are the due dates for all assignments. There's way too much to make you do this Wednesday, so what we do next Wednesday, I want to give you just over a week to work on it. Things to note about assignments in this class. They're long and they're complicated. Start early, come to me with questions. I love talking about this stuff. So I have office hours. I would love to see you in those office hours to answer any questions you have as you start working on that. You should be able to do at least the first bit of this assignment. Starting now, the very first question has you writing some grammars, kind of like we wrote them on Friday. So you can get started with the assignment. It will cover stuff that we haven't seen yet. You should be able to do all of it by probably Thursday or Friday of this week. The other thing that may happen, because the last time that I taught this, the quarter started on a Monday rather than a Wednesday, so I may be off by a couple days. At some point this quarter, I may decide, oh no, in order to make sure that everything is done, I may assign something else later in the week and have some overlap between assignments. That's just the unfortunate nature of that. I will always try to give you at least a week to work on any given assignment. I'm not gonna assign something on Monday that's due a couple days later and is a lot of work. But do note that because it's a lot of work, you will want to start early. If you start a couple days before it's due, you're going to be in massive crunch time, needing assistance for just about every question probably to make sure that everything is in on time. They're designed such that you will be doing a lot of thinking on your own, a lot of problem solving. So there are multiple right answers to most of these problems. It's not quite like math where you need to exactly come up with a right answer. If I'm asking you to design a system, there will be multiple systems that answer the problem correctly. There may be one best answer, but I'm never going to rely on or expect that you produce the best answer unless the problem specifies it. But we'll talk more about it as we get there. We'll start talking about our first kind of automaton. Any questions before we dive into deterministic finite acceptors? I'm gonna start with something in this slide deck that is pretty gross. We're gonna come back to this after we've talked about it. Here is the formal definition of a DFA. We're gonna start taking deterministic finite acceptor and calling it a DFA. So we see a quintuple, which is just a tuple with 5 elements. This machine, M, is going to be defined by these 5 components. We need a set of internal states. Each of these states define one of those kind of places in the program if you were to imagine the DFA as a program. Kind of like we talked about with the transducer of a binary adder that we wrote, there was a state for each one of the possible input pairs. So we need to define the set of states. We need to know what the input alphabet is. So this is just the set of symbols that can appear in the input alphabet. That is your sigma. Delta is your transition function. It's going to tell us for every possible pair of internal states and input alphabet symbols. So that's a cross product we talked about on the first day. Just think of it as every possible pairing of an internal state with a symbol for the input alphabet. We need to define the successor state to that. So if the input is a 1 and a 0, the successor state is going to be that something. We need to know where to go when we see that pair of internal states, input alphabets. Of all of the internal states, we need to know which one we start at. Think of this as the place, the state that you're in when the program starts. It has to start somewhere. We don't want it to start in different places. And then we need a subset of those internal states that we're going to declare final states. Since this is an acceptor and not a transducer, the final states tell us if we finish reading the input string and we end in one of these final states, then we accept. If we finish reading this input string and we are not in one of these final states, then we reject. There's a lot there. Again, we're going to come back to this at the end and hopefully with some understanding and some practice problems under our belt, this will make more sense. Are there any clarification questions on this before we dive into visualizing it and some practice problems? All right, what can we do? We're going to start by labeling our states. Q sub 0, Q sub 1, Q sub 2, Q sub 3, etc. As we start defining actual problems to solve, we can name these states more like what the actual name of the state is. Kind of like a variable, we can name the states better than this. But for now, they're just going to be a sequence of states. We start with the input mechanism, whatever's going to be reading from the input at the leftmost symbol in the input string. As we transition, this input mechanism will move character by character through the input string, one at a time. We cannot jump around, we cannot move forward multiple characters, we cannot go back. One way that you might see this transition, an element of this transition function written is something like this. So this should be read, the transition from state Q0, if we're currently in state Q0, and the input character, the current input character is an A. Then the output state basically is Q1. We're going to transition from Q0 to Q1 on an A. So that may be one way that you see this written. In English, if the DFA is in state Q0 and reads an A from the input mechanism, it transitions to state Q1. So you can define the DFA as just a sequence of these transition functions. That's how you would define that delta, is through taking every possible pair of state, character, and defining what the transition is to. It can be to itself, a state can loop to itself, a state can move to another state. It's much easier to visualize if you actually draw out a transition graph. So let's take a look at an actual transition graph where our vertices are going to be these states and our edges are going to be all of these transitions defined by the transition function. So Here's an example. Let's see, there we go, an actual image. So let's start by looking at this. Q0 is the start state. You can see this by the fact that there is an arrow pointing from nothing to this state. So this says, regardless of what the input string is, the initial state that we're going to be in is Q0. We need that arrow there, and it's something that I will probably forget a few times throughout the class. I'll just start naming or numbering states, assuming that Q0 is the initial state, but we need that arrow there to show this is where this begins. A final state is denoted by a double circle, a circle with a circle inside of it. So if we see this, we know that if at the end of the input string, we end up in this state, then we accept. If we end up in some other state that is not final, in this case, either Q0 or Q2, we reject. This is much easier to read than a long list of transitions. It actually allows you to kind of take in everything at the same time visually. It's much easier than what you would actually write in a text file if you were going to define one of these. So let's actually go through an example. So the input alphabet is binary. Let's say we have an input string 0, 1, 1. Does anyone want to volunteer to attempt to reason through what this system does step by step as we do this? Yeah.
So it'll start at Q0 and it'll go back to itself. And then it'll go to Q1, it'll go to Q2, and it'll accept it.
So we start at Q0. We see that I wrote an arrow on the board stating the current input symbol. So in a DFA, there is only one possible transition from this state on a 0. So we're going to look for what output edge has the label 0. But in this case, the transition from Q0 to itself is what consumes that 0. So we're going to transition from Q0 to Q0 as we consume this 0 in the input string, which will move us to here. So we move forward one position in the input string, and we transition from Q0 to Q0 as we consume that 0. Continuing, now the current character is a 1, so we're still in Q0. We read that 1, we're looking for the output edge, the outgoing edge from this state. We see that we transition from Q0 to Q1 on that 1. So we're going to move from Q0 to Q1, that's the current state. This now moves to here. From Q1, when we read a 1, where do we end up? Q2. So we're going to move from Q1 to Q2, and we will consume this 1. We now determine we are at the end of the input. Are we in a final state? We are not. So this string gets rejected. It is not part of the language that this DFA accepts. The next question that I might ask you is a lot more abstract. So does everyone understand how to parse an input string with one of these? What language does this DFA accept?
Binary.
It's some binary, but it's not all binary, because this is a binary string, right? And it gets rejected. So what subset of binary does this machine accept? Basically, how can we find out what do all strings have in common that end in state Q1? An odd number of ones, that is correct. This has 2 ones in the input, which is even, so it gets rejected. So what's a binary string with an odd number of ones?
Zero, one, one, one.
0, 1, 1, 1. We could see that we go 0, 1, 1, 1, and we go back to Q1, so that would be accepted. And you see that no matter how many leading zeros we have, we will stay in Q0 until we see our first one. Once we see our first one, we're in an accepting state. So far, we've seen an odd number of ones, so we accept. As soon as we see a second one, we are going to transition to Q2. But note that if there were other zeros in the meantime, I don't know. We see a second one there, we're back. So the string 0, 1, 0, 1 that has an even number of ones gets accepted. So that's a good guess, but we found a counterexample to it. I actually use this example because it's phenomenal for showing that intuition often falls apart on later use. So at first glance, it very much looks like this is an odd number of ones. This is why you can't just come to a conclusion, run with it, and then move on. Especially in this class, you're gonna have to start thinking, okay, is there a counterexample for this? Does it work in all cases? So that's interesting. We will find the tools to figure out exactly what language this accepts momentarily. Other abstract questions. A DFA accepts one and only one language. Why is that? Yeah,
Maybe because some rules of the language are what defines the paths.
yeah. Yeah, so there's gonna be some number, probably certainly infinite, that are going to lead to some accepting state. But we define this based off of what subset of the star closure of the alphabet gets accepted. There will be some way to define that. That is the definition of a language, basically. A language is some subset of that star closure. Is it possible to have 2 different DFAs that accept the same language? Basically, is a DFA a unique structure for a particular language? Kind of the other way around. So this was yes. Thoughts on this?
No, like everything has to be like really unique for that.
Good intuition. Anyone agree? Disagree?
Can't think of the example, but I'm sure that for a suitably complex language, there'd be some technically different way of representing it.
That's correct. In fact, there are often an infinite number of DFAs that you can construct that accept the same language. The way that I like to think about this is, could you write 2 different programs in Java that have the exact same function between input and output? If I assign a lab, is everyone going to submit exactly the same program as the solution to that? Or could you come up with 2 separate programs that do the same thing?
You definitely probably a couple that do the same thing.
Yeah. Usually an infinite number. But yeah, you can just do a no up, basically, some arbitrary number of times, do nothing, just semicolon. If I do that once, twice, 3 times, 4 times, 5 times, they're now all separate programs, or distinct programs, that all do exactly the same thing. So the answer to this is also yes. So if at any point I ask you to construct a DFA, you don't get exactly the same DFA as your friend, somebody else. There's no guarantee that one of you is wrong. You may both be right. Would we like some example problems to get some practice writing and analyzing some DFAs? Now these guesses float in the middle of nowhere and make no sense. Okay. Find a DFA recognizing the set of strings on our alphabet AB that start with the prefix AB. One thing about a DFA, every possible transition needs to be defined. So if you have a particular state, you need an outgoing edge from that state on an A and on a B for every state. So remember that we need to figure out what is the initial state. The whole set of states. The transition function. The set of final states. And of course, the input alphabet is already determined for us. So this is that quintuple from before. These 4 things plus what is given. Just draw this as a transition graph. Don't try to give the entire full formal definition of it, but your drawing should consider all of these things. Whenever I throw something like this back to the class, feel free to talk to your neighbor, introduce yourself, work in small groups. There's something that says that this has to be an individual thing. If you prefer to work with someone, let it be known and find someone else who would also prefer to work with someone. And have any questions or confusions as they've gotten started? So we know we need to start at some initial state, Q0. People think they have an answer yet? Just curious how it's going. About half. Let's walk through the logic, and that way you can, if you got stuck somewhere, perfectly fine, we're brand new at this. Let's see if we can think about the difference between your thought process and how other people have constructed a solution. So we know we have a couple of potential branches from here. We either read an initial A or we read an initial B, which is the way that I like to think about it. So which of these is easier to handle? Reading an initial A or reading an initial B?
Reading an initial B to the, she's done.
Yeah, I love it. I think exactly the same way. So we know that we need to accept the prefix AB. If the very first character is a B, there is no way that anything that follows can make this be in the language. So we're going to define the transition on a B. We're going to call this on a B, going to state Q1, and this is what we're going to start calling a trap state. This is a state where if you reach it, Admiral Akbar pops out of nowhere, says, it's a trap, and then it just loops that literally forever. There's no escaping Admiral Akbar's trap. So for it to be a trap state, the definition of a trap state is that we need a transition for each input alphabet character. So you can choose to draw this in a couple of different ways. We're going to loop back to itself on an A and loop back to itself on a B. This is the more verbose way of drawing this. You can add a multi-edge to a single drawn edge, making this a little bit easy on yourself, and comma separate any input characters that you would read on that same edge, as long as they have the same destination. The same source, the same destination. This just says on an A or on a B, we transition from Q1 to Q1. It's a trap because no matter what follows, we are not escaping Q1. It is a black hole that sucks the rest of the input alphabet, the rest of the input string. We're not ever escaping from Q1. This is what you do if you find that you're in some way, some state that you cannot ever accept from. All right, going back to Q0, because we haven't defined what happens from Q0 on an A. So it's not a full transition function. In order for it to be a full transition function, follow the algorithm for every state, there must be an outgoing edge defined for every alphabet character. So we need something that we're going to do on an A. Should we visit this trap state on an A? No, because there may be a way that we accept from there. So we're going to need to define a new state for this. There's no way that we can handle this on Q0. Well, maybe not. What would happen if we looped from Q0 to Q0 on an A? That would be one other consideration. It's not the correct consideration, but why?
You started with the two A's, it would accept the string.
Well, that would be fine. We want the prefix AB to be what we, but what if the string was exactly AB? What would happen? On an A, we would loop to Q0. And on a B, we transition to Q1, which is not an accepting state, it's our trap state, but we want to accept AB. So that's the hint that tells us we should not transition from Q0 to itself on an A, because there quickly becomes a counterexample of something that we would need to deal with in this case. So that tells us we probably need an additional state. So we're going to now transition from Q0 to a new state on an A that we're going to call Q2. To have a full transition function in this DFA, we need to define what happens from Q2 on an A and on a B. Which of those is easiest to define? An A. If we start with AA, there's no way we can possibly accept. Do we have a state already that is basically the equivalent of there is no way we can possibly accept?
State Q1.
Q1, it's a trap. So we're gonna make this transition on an A. And we can utilize something that we've already made. Already defined. What happens on a B? Is there anything that we have so far to tell us the state, kind of the meaning of that state? We've seen AB. First of all, we want to accept that string by itself. None of these states so far have been final states because we haven't reached a point where we've seen a prefix AB. So we need to define exactly what that looks like. So we're gonna have to transition from Q2 on a B to another state, Q3. We're gonna make a final state. We make it a final state because AB is in the language. But we don't have a complete transition function. What should we do?
Make Q3 point to itself on AB.
Yeah. We're gonna make a transition from Q3 to itself on an A and on a B, because once we reach that point, no matter what happens from there, we saw that prefix. Now we have a complete transition function. For each state, there is an outgoing edge on an A and on a B, which tells us for any given input string, precisely where we're going to finish. We know exactly what will happen. It's pre-described what will happen given a particular input string. So unfortunately, we are out of time. Does anyone have any questions I can answer while people pack up and you're ready to go? How can I help this make more sense for the moment? We'll get more experience with this tomorrow, but I want to leave on an I understand this note. Hopefully. Questions, concerns, considerations? All right, if you have any confusions, I'm heading back to my office for some office hours. Feel free to stop by. I can redraw this and we'll go over it in more detail. See you tomorrow for some additional fun stuff. This is more fun than the other stuff.